Hello everyone, I'm Vishal Akula and this is my presentation of SIT718 Real World Analytics. Today I'll walk you through my analysis and modeling processes based on a red wine quality dataset. We started with the red wine dataset of 1599 observations. For this project, we selected a focused subset of 460 samples and used 5 key variables. They are citric acid, chlorides, pH, alcohol, and quality, where quality is our target variable. Here we visualized the data using histograms. The chlorides and alcohol variables were skewed. Quality rating were mostly 5 or 6, showing limited variability. Understanding distribution is essential for choosing the right transformation. Here, these are the histogram graphs for the 5 key variables. These scatter plots revealed relationships and patterns. Alcohol showed a stronger positive correlations with the quality, while others like citric acid had weaker or less clear influence. So transformations normalize values, reduce skewness, and helps models converge better. For instance, log or square roots can stabilize skewed data, while scaling puts variables on equal footing for model fairness. So here we normalized all inputs between 0 and 1. This ensures consistency and improves the performance for models like WAM and WPM, which are sensitive to scale. So, for modeling techniques, we implemented 4 aggregation models. They are weighted arithmetic mean, which is WAM, and weighted power mean, which is WPM, with the P is equals to zero point 0.5 and P is equals to 2, and ordered weighted averaging, which is OWA, and each was tested for accuracy using RMSE and correlation. Then error measures and correlations. Among the models, WPM with P is equals to 2 outperformed the rest. It had the lowest errors and highest correlation with true quality values, making it our best choice. Here, the best fitting model is WPM2, where it stood out with an RMSE of 0.1719, Pearson correlation of 0.4094, and a Sperman correlation of 0.4845. These indicates both accuracy and consistency with the actual wine quality. When looking at weights, alcohol emerged as the most influent feature in all models. This aligns with the idea that higher alcohol content generally contributes positively to wine quality. Here, alcohol was highest contributor across all models, and the chlorides were neutral in some models but significant in OWA. Excessive saltiness can reduce wine quality, and this variable captures that effect in the modeling. So next, pH and citric acid. pH was moderately influential. A lower pH, meaning higher acidity, is often desirable for freshness and balance, especially in red wines. Citric acid. Citric acid had the least consistent influence. The sensory impact is subtle and depends on the overall wine composition, explaining the lowest weight. To test the model, we input a new wine with given values. The predicted quality was 3.55, suggesting a low to moderate rating. This aligns with expectations based on variable effects. This prediction made sense. The alcohol was below average and the high chlorides could hurt flavor. The model's prediction was in line with known wine chemistry and higher quality wine. From our analysis, a higher quality wine would typically have higher alcohol, lower chlorides, a lower pH, and a balanced citric acid profile. Model limitations. Despite its strengths, our model has limitations. It's linear and the small dataset restricts generalizability. Also, transformation can make interpretability harder. Ethical modeling is crucial. Predictions shouldn't mislead customers or influence pricing unfair. Transparency, data protection, and fairness must be upheld in real world deployment. Thank you for your time. I hope this presentation gave you insights into wine quality predictions using real world data analytics.